Hello friends, welcome to the second video lecture on digital design using Verilog for Absolute Beginners. In the first video, we have understood what is digital design and what is the need of Verilog and what is the structure of Verilog, especially module, what are the parts of the module, and we know that a module has two parts. One is the declaration, the other is body. We have taken some examples also. In the declaration part, we declare the name of the module, I/O ports, input and output ports, and in the body, we'll explain the relation between output and inputs. And every module will end by the statement end module. For this, you have taken one or two examples also in the earlier video. In this video, I try to explain you what is the meaning of this register transfer level model. According to my observation, many of the people who are learning this Verilog HDL have a common doubt in their mind. What is this RTL? Because majority of the trainers use the word RTL model. So in this video, let us understand what is actually the meaning of RTL model and what is its relevance in the Verilog course and how this is useful in the design of a digital system. Okay? Yes, let us start. To understand this RTL, let us recall that the digital circuits are two types. One is a combinational, the other is sequential. When compared to the combinational circuits, the sequential circuits are a little bit complex. This is the common opinion of many of the students. Another important thing is a digital system is a sequential logic system with flip-flops and gates. It's quite natural. Any digital system, mostly a sequential logic system with flip-flops and gates. Normally, to analyze these circuits, we use state tables. Of course, as long as the digital system is simple, with a minimum number of subsystems, there will not be any problem in the design using state tables. But as the digital system becomes complex, for example like a microprocessor, for example like any microcontroller chip, or any MIPS processor, or any RISC processor, anything, any such complex systems, then the state table method becomes very cumbersome. It becomes very difficult to analyze or design the system. So normally what the engineers will do, they will adopt a modular approach. That is, the complex system is partitioned into modular subsystems, each of which performs some function. For example, let us take your microprocessor. We know microprocessor is a very complex system, but it can be divided into smaller subsystems like ALU, registers, counters, memory, and so on and so forth, bus, etc., etc. In the same way, any complex system can be considered as a combination of many subsystems or modular subsystems. These subsystems are also known as modules. Modules are constructed using digital devices like registers, multiplexers, decoders, ALU, and control logic, as I've just explained. So how do you construct a module? They are constructed using devices like registers, multiplexers, decoders, ALU, control logic, etc. Let us discuss in detail. So, in a complex system, we know that there are many subsystems or modules. And once you have various modules, these modules must be interconnected with the data paths and control signals to form a complete digital system. So we can say now a complex digital system is nothing but large number of modules interconnected with data paths and the control unit which generates the necessary control signals. So a digital system can be best defined by a set of registers and the operations that are performed on the binary information stored in them. What do you mean by that? When I say I have a register I will always store the binary information. The value that is stored in a register will be either in terms of ones and zeros. That is, it may be like 1011 or simply 1 if it is a 1-bit register. If it is a 4-bit register, it may have starting from 000 to 1111 and so on. So you will have binary information stored in the registers. And once I have some data in the registers, there must be some operations that are to be performed. What are the operations performed on the registers? Load operation, shift operation, count operation, clear operation, etc. So the information flow and processing performed on the data stored in the registers are referred as registered transfer operations. Registered transfer operations. That means if I have some data in one register, I can transfer that data, shift that data, move that data from one register to other register. In this case, if there is no data, I can load the data into the register. If I need, I can shift the data either left or right. I can also increment the data, count. When I don't want, I can clear the data. So what are the operations that are performed on these registers? Load, shift, count and clear, etc. Now, there is no meaning for this diagram, just only to explain that when I have a simple, that is, it is a complex system, does some processing and finally gives a result, and this will be stored in another register. If you see the whole example here, you have registers, multiplexers, flip-flops, something like a processing elements, etc., which process the data that is given. So a digital system is denoted at the register transfer level and specified by the following features: the set of registers in the system, as you have seen, the operations that are performed on the data stored in the registers, and the control that supervises the sequence of operations. This is the most important thing. Normally in a microprocessor, we call this as a control unit. Based on the signal that is given by the control unit, the sequence of operations. That means what is the operation that is to be taken now? And after the next minute, what are the operations that are to be taken? So these things will be done by the control signals. We'll see in detail in the next slide. First of all, again I go back. What is this register? A register is a set of flip-flops that stores binary information and has the capability of performing one or more elementary operations. As I've already told you, this is purely for absolute beginners. I am repeating some of the concepts where you will have a clear idea what is the relation between digital design and the RTL model, register transfer level model. Why this model is being preferred? Because I repeat, every digital system somehow or other is a combination of registers, and the entire process will be transferring, shifting, loading the data based on some control signals. That's why I have again come back. What is a register? A register, those who knows the basics of digital electronics, they can easily understand that a register is a set of flip-flops that stores binary information, and has the capability of performing one or more elementary operations. Just now I have explained. A register can load new information. You can load some data into the register or shift the information to left or right. Similarly, a counter is also a register, as you know, that increments a number by a fixed value. Say for example, say by 1. Increment. When I use the instruction increment, it will increment the data by 1. Decrement the register. Decrement by 1. Similarly, a flip-flop. A flip-flop is also a 1-bit register. Most popularly, it is known as a latch, or in analog electronics, when you say the analog electronics, it is like a bistable multivibrator. What it can do, it can store only 1 bit of data. That means this bit can be either set or cleared. Most of the bit operations that you have seen, so you might have come across in the basic digital electronics. So a flip-flop is a register, a counter is a register, so a memory is a register. So when you consider this digital system, majority are the registers. Next, the control. In a digital system, the operations are discussed earlier. Load, shift, count, increment, all these things. The operations discussed earlier are controlled by timing signals, which sequences the operations in a prescribed manner. They will keep them in an order. These timing signals will keep these operations in an order. We'll discuss this further. Certain conditions that depend on results of previous operations may determine the sequence of future operations. That means, based on the output of a register, it may become input for the next register or next device. So it may decide the future operations also. The output of control logic are mostly binary variables, which initiates the various operations in the system. That means, what is the meaning of this control logic or binary variable? What is the meaning of this? When it is 1, it will do something. If it is 0, it will do something. Or if it is some other value, it will wait for something. So these are all output control logic or binary variables. Now let me consider a simple example. With this, I think the concept will become more clear. You have to thank Maurice Mano. I have taken this material, digital design by Maurice Mano. He has explained wonderfully the concept. Let us take in a simple case. So here I have shown R2. So R2 transferred to R. R2 arrow mark, left arrow. R control signals are given by some state machine, finite state machine. And we know that there are 2 types of state machines based on the timing. One is synchronous, the other is asynchronous. What is this synchronous machine? We are now interested in the synchronous machine. So synchronous machine, the operations are synchronized by the system clock itself. A statement that specifies a register transfer operation implies that a data path is available from the output of source register to inputs of the destination register. That means, once you say that there is a register transfer operation in a system, what it automatically implies, there is some necessary circuit, a set of circuit connections. That is called a data path. What it will do? These circuit connections will give us a facility that the outputs of the source register, for example R1, and they are given to the inputs of the destination register, earlier example R2. That means many times this may also have a parallel load capacity. That means if I have an 8-bit data, all the 8 bits may be transferred from R1 to R2. But of course, there are also some cases where the data is being transferred serially between the registers. How do you transfer this serially? Bit by bit, bit after the bit, repeatedly shifting their contents along a single wire, 1 bit at a time, which we normally call the operation as a shifting operation, shift left or shift right, etc. So whenever you take these operations require some control. Therefore, these operations are expected only under predetermined condition, but not at every clock. That is the most important thing. These transfer need not occur at every clock, but they occur at clock transition. We'll see that in the next slide. So how this, and also this transfer, this control is normally represented in terms of your Verilog code, etc. Something like a conditional statement. Say for example, if then statements. Let us see this. Example, if T1 is equal to 1, then R1 transfers the data to R2. Earlier it was only R the clock transition. This is the most important thing. Many times what happens? The condition control T1 is equal to 1, it may become. But the clock, the most important thing is the clock transition is important. Till then, the transfer do not takes place. That means, suppose we say the transfer must occur from at a transition of 0 to 1. During that transition alone, or until that transition reaches, only the transfer of data takes place. Until then, it has to wait. Another most important thing, a comma may be used to separate two or more operations that are executed concurrently. Normally, most of the operations here are concurrent, means parallel. They take place at the same time. Of course, in the next coming videos, we will discuss in detail what are these concurrent or concurrent operations. Here a simple example. If T3 is equal to 1, that is time is equal to 1, then two transfers are taking place. R1 is transferred to R2 and R2 is transferred back to R1. That means parallelly at the same time, when this transition T3 is equal to 1 takes place, at the same time R1 data is moved to R2 and at the same time R2 data is also moved to R1 or transferred to R1. This simultaneous, that is parallelly, concurrently, this data transfer will take place. This statement specifies an operation that exchanges the contents of two registers, and both the registers are controlled or triggered by the same clock edge. That's very important. Instead of a fixed T3 is 1, not only is T3 is equal to 1, that transition is also equally important. This simultaneous operation is possible with registers that have negative edge triggered flip-flops. Especially that's why we have another interesting thing. When we consider the flip-flops, these flip-flops operate based on the clock transfer. The data is transferred to this. Next, increment operation. That is called a count. I have a register R3. I want to increment it by 1. Then what do? I use the instruction increment. So when I increment this by 1, this will become R3 plus 1, but the content of the R3 plus 1 is again in R3. Similarly, I want to shift the content of register R4 by 1 bit. SHR, shift right the content of R4 by 1 bit, and it will be stored in the same register transfer. That's the simplest thing. That's why such models are called register transfer level, RTL, register transfer level model. Here I consider these register concepts. R5, 0 is transferred to R5. What is the meaning of this? Register R5 is cleared to 0. The type of operations that perform commonly used in digital systems can be classified into 4 types. What are the operations now? Transfer operations. Similarly, arithmetic operations, which perform these. Earlier, second one. First one is addition. Second one, increment. Then logical operations, performing logic OR, logic AND. And earlier you have seen shift operations, where we wish to shift the data between the registers. So the transfer operations does not change the information content. Very important. When you have seen in your microprocessor move A comma B, the contents of B are copied to A, which normally we call at a lower level accumulator. Move A comma B, contents of B are moved to A. That means that is a transfer operation, register transfer. So in the transfer operations, the data is not changed. The content of the register is not changed. But in the remaining other operations, 3 operations, when I perform logical operations or shift operations, increment operations, etc., there is a change of data, change of the information during the transfer. I hope you have understood this clearly. Thank you very much for your patience.